So we've been looking at solving different types of equations. So far, we've looked at solving linear equations and quadratic equations. So now we're jumping into the complex number system. And so we want to look at the complex number system because right now, when we're looking at the real number system and we square a real number, we always get back a positive number. And so to deal with that situation, I don't know who came up with it, but some mathematician came up with the complex number system. And so this gives us a chance that if we square something, it comes back out a negative number. So after I go through this topic, I'm hoping that you'll be able to add, subtract, multiply, divide complex numbers. And then I hope that you'll be able to solve quadratic equations. And when you get a negative underneath that radical, you'll realize that there is a solution, and it's a complex number, which is the solution. So I am just going to bring the screen up in here, just so that I didn't have to write everything out and just go through it really quickly. So if you're looking at your imaginary unit, which we denote as I, this is a number whose square, so if we square I, we get back -1. That is, again, I squared is equal to -1. So you should know that complex numbers, they can be written in this form of A plus BI, where we say that A and B, they're real numbers. The real number A is called the real part of the number. So the part that is not attached to the I. And I is the imaginary unit. So when we write numbers in the form of A plus BI, where A and B are real numbers, it is said to be in standard form. If we don't have the real part in there, we don't have that A, and we just have BI, then we say that it's just a pure imaginary number. So I squared is -1. If we take the square root, let me just write this. So we said I squared was equal to -1. If we take the square root of -1, that is equal to I. So if we get a negative underneath our radical, we would say that that is I. So just going back to properties of radicals really quickly, if you have some square root and you can break down your number into factors, so maybe we can break it down into multiples of A times B. Recall that this is the same thing as the square root of A times the square root of B. We have to put in one little stipulation in here that A and B are not both negative. So we can go in the opposite direction. If we had square root of A times square root of B, we could, same index in there, we could multiply what was underneath the radical together to get the square root of AB. But again, A and B can't both be negative or that won't work out. And I can show you an example of that in a moment. So looking at the following and knowing that the square root of -1 is I, we have the following examples. So we have the square root, let me just keep this here for a second. we have the square root of negative 49. And so just like I have broken that up, normally I wouldn't break this up like this, but we can say this is the same thing as the square root of 49 times negative 1. So we can break it down, square root of 49. So what number do I square to get back 49 is just 7. And the square root of negative 1 is I. So the square root of negative 49, we would say, is 7i. So part B of this question is asking us to find the square root of negative 27. So 27 is not a perfect square, but there's factors of 27 that are a perfect square. So let's rewrite negative 27 underneath the radical as factors, one of those factors being a perfect square and one of them being negative 1. And so we can break down the square root of negative 27 as I know 9 times 3 is 27 and 9 is that perfect square. So we have 9 times 3 times negative 1. So I can pull out the pieces, square root of 9. Well, what I square to get 9 is 3. There's no whole number I can square to get back 3. So I'm going to keep that underneath the radical. And I know that the square root of negative 1 is I. So we have 3i root 3. So a lot of times when we're pulling values out of the radical, we put them in front of the radical. That way there's no question if that value is under the radical or not. So one more, looking at the square root of negative 125. So again, there's no number that I can square to get back 125. I'm just ignoring the negative at the moment. If you guys forgot on how to figure out if there's a perfect square in that, then you want to look at your number and doing prime factors. So you can kind of make your tree here. And so I know because it's ending in 5, at least 5 goes in there. And so 5 goes into 125, it ends up going in 25 times. To me, I would stop here just because I noticed that 25 is a perfect square and 5 is prime. But if you wanted to, you could break that down as 5 times 5 and then group things in pairs to look at that. So square root of negative 125, I'm going to rewrite as 25. Maybe I can write negative 1 here. Negative 1 times 5. So going through and pulling out the perfect square, the square root of 25 is 5. Square root of negative 1 is I. And then we're left with square root 5. So in each one of these cases, these were pure imaginary number. There was no real part to that complex number. If it asked you what the real part was, we would say it's 0. If it asked you what the imaginary part is, when you're telling the imaginary part, don't tack on the I. So for part A, our imaginary part would be just 7. And part B, our imaginary part is 3 root 3. And for part C, the imaginary part of that complex number is 5 root 5. So for this next video, we want to write this complex number in standard form. So we're simplifying this down. We're pulling out the parts underneath the radical that are perfect squares, or rewriting the square root of negative 1 as I. So looking at this, I have 4 minus, and then the square root of negative 36. Well, square root of 36 is 6, and the square root of negative 1 is I. So we get that the standard form of this complex number is 4 minus 6i. So again, if we're asking for the real part, in this case, this is 4, But the imaginary part, we would say, carry the sign in there, it's -6. We don't put on the I when we're just saying the imaginary part. And that's where students usually get that wrong. So part B, looking at what is -5 plus the square root of -32. So we want to break down 32 so that the factor of -32 has the largest perfect square. And so if you don't see that, again, you can break it down as prime factors and then pair your combos that are repeating. 16 times 2 is 32. And so I could break this down as 16 times -1 times 2. So bringing down my -5 plus taking the square root of 16, we get back 4, the number I can square to get 16. Taking the square root of -1, I get back I, and then I'm left with square root 2. And the last one in here, we have 3 minus, well, 25 is a perfect square. And so square root of 25 is 5, and then it's square root of -1 is I. So we can say that two complex numbers are equal to each other. So we would say that A plus BI is equal to another complex number, let's say C plus DI. This is the case if and only if. So if and only if in mathematics, a lot of times we'll write it as IFF. So that means if and only if the real part A of the left-hand side is equal to the real part, B, but I want C of the right-hand side. And then the imaginary part on the left-hand side, B, is equal to the imaginary part of the right-hand side of the equal sign, which is D. So these two complex numbers are equal to each other if and only if the real parts are equal to each other and the imaginary parts are equal to each other. So if we were looking at adding complex numbers, all you're doing is kind of treating I like the variable. So you're adding your real parts together and you're adding your imaginary parts together. So for instance, let's look at an example. If you had the complex number 4 minus 7i, and we were adding that to the complex number, let's say 6 minus 4i, well, technically, I don't need those parentheses because what's outside of that parentheses is a +1 in each case. And so we can actually drop the parentheses and rewrite it as 4 minus 7i plus 6 minus 4i. And so now we're looking at summing the real parts together. So 4 plus 6, which is 10, and summing the imaginary parts together. So carrying the sign, so a -7i minus a 4i. So they're both negative, so I'm going to add the numbers, and the result's going to be minus or negative. So 7 plus 4 is 11. So this is the result of this complex number by simplifying is 10 minus 11i. So notice there's a difference where if we were looking at the following example, let's say -7 minus 8i. And then we had, let's say, minus 3 plus 6i. So in this case, I can't just drop my parentheses on that second grouping because of this minus sign out here. So if you have a negative sign outside or a number outside of that parentheses and it's telling us to multiply what's inside that second parentheses by -1. So I can basically drop my parentheses on the first complex number. So -7 minus 8i, distribute my negative into the second parentheses. So -1 times 3 is -3, and -1 times 6i is -6i. So combine our real parts together. -7 minus 3 is -10. And I have a -8i minus a 6i, which gives me -14i. So now let's look at a case where we're multiplying two imaginary numbers. And so let's say we have the imaginary number a plus bi all times the imaginary number c plus di. So we're just going to multiply like we were multiplying two binomials together. And so we're taking each term in that first parentheses and distributing it to each term in the second parentheses. So I would look at a times c, which is just ac here, a times di, so plus a di. So I distributed that first term to each term in the second parentheses. Now distributing the second term to each term in the parentheses, I have bi times c. So I'm going to write it as bci. Plus, I have bi times di. So that is b times d times I squared. So by definition, I squared is -1. And so let's rewrite that I squared as -1 in this expression, and let's regroup our imaginary parts and our real parts together. So I have this AC here. This right here, I squared is -1. So the I is going to go away when I square it. So this is going to give me minus BD. And then let's group the imaginary parts together. So I have plus ADI plus BCI. So I can technically, if I wanted to, I could group the real parts together. AC minus BD is my real part. Plus, for the imaginary part, I could factor out the I. And so this would give me, pulling out the I, I'm going to pull it out behind. Pulling out the I have AD plus BC times I. So the real part in this case is AC minus BD. The imaginary part in this case is AD plus BC. So the next example in front of us now has numbers in there, and we're multiplying two complex numbers. We're multiplying the complex number -4 plus 8i times the complex number 2 plus 7i. So let's distribute. -4 times +2 gives us -8. And -4 times 7i. Well, -4 times 7 is -28. And then we have the I. So distributing our next term, 8i, to each term in the second parentheses, we have 8i times 2. So this is plus 16i. And we have 8i times 7i. Well, 8 times 7, that's plus 56. And I times I is I squared. but I squared is -1. So we could rewrite this as -8 minus 28i plus 16i minus 56. So writing it in complex form, we want to write the real part first. So summing our real parts, -8 minus 56, this is -64. And summing our imaginary parts, so summing -28i plus 16i. Opposite sign subtract, 28 minus 16 is 12. Larger number has a negative, so it's minus 12i. So a lot of times in mathematics, we take a binomial. So that's a, well, it's so a binomial having two terms and multiplying it by its conjugate. So if z is an imaginary number, a plus bi, we say the conjugate and we write the conjugate mathematically with a horizontal line over the variable. So, and we say z bar. So the conjugate of z bar, is equal to, all you're doing is you're changing the sign in between the real part and the imaginary part. So in this case, because it's a plus in between the real and the imaginary, I would put a minus in between. So the conjugate of z is a minus bi. So notice if we multiply the conjugates together, well, this would be a plus bi all times a minus bi. So you should be able to do this without going through and distributing like we were doing before. If you're multiplying two conjugates together, recall so usually when we were factoring, kind of go backwards. When we were factoring a difference of two squares, this was equal to the factor of a minus b, a plus b. Or you could have written that as a plus b, a minus b. A minus b and a plus b are conjugates of each other. So if we're multiplying two conjugates together like that, notice that you're just squaring the first part and you're squaring the last part. So if I square my real part, which is a, minus squaring my imaginary part, bi. So this is going to equal a squared minus bi times bi is b squared I squared. But recall I squared is -1. So this is going to be the same thing as a squared minus b times -1. -1 times negative b is positive. And then it should be b squared. So -1 times b squared is positive b squared. So distributing this out, we get a squared plus b squared. And this is going to be helpful soon when we're starting to divide by imaginary numbers. We need to use this rule to help us get rid of the imaginary number in the denominator. So let's look at a couple of these examples to help us. So our next example, we're given that z is equal to 4 minus 3i. If it says find the conjugate of z, So find z bar. This is just changing the sign in between the real part and the imaginary part. So the conjugate of z in this case would be 4 plus 3i. So let's say that was part B. I'm sorry, A. And part B is z times z bar. So it's saying we want to multiply 4 minus 3i all times 4 plus 3i. So using the fact that they're conjugates of each other, we can square the first term minus the square of the second term. So 4 squared minus the quantity 3i squared. Well, 4 squared is 16 minus 3i times 3i is 9i squared, which ends up being negative 9 because I squared is negative 1. And so 16 minus negative 9 is 16 plus 9, which is 25. So multiplying the conjugate of two imaginary numbers together, we get a real number. So that's going to help us when we're looking at division of complex numbers. So if you're dividing by a complex number, we want to get rid of the complex number in the denominator. So for instance, let's say that you had 2 all over 3 minus 5i. So if you're dividing by a complex number, what you want to do is you want to multiply by a fancy one. And that fancy one that we're using is going to be the conjugate of this imaginary number. So the conjugate of 3 minus 5i, remember we had just changed the sign in between the real and the imaginary. So 3 plus 5i. 3 plus 5i. So let's distribute our 2 to each term that we're multiplying. 3 plus 5i. So 2 times 3 is 6, plus 2 times 5i, which is 10i. All over 3 squared minus 5i, quantity squared. Well, 6 plus 10i, those one's real, one's imaginary, so we can't combine it. 3 squared is 9, minus 5i times 5i is 25i squared, which is negative 25. So I have a minus and negative 25. So it's really going to end up being plus 25. So I have 6 plus 10i all over 34. So a lot of times it asks you when you're doing your homework, and if you were doing this on an exam, I would want the simplified form. So I notice we have like factors in the numerator that's going to cancel with the denominator. So before I can start canceling, let's pull out what we have in common with 6 and 10i. Well, 6 and 10 both have a 2 in common, so we can pull out a 2 from both of those terms. And if I pull out a 2 from 6, I'm left with 3. And if I pull out a 2 from this 10i, I'm left with positive 5i. All over 34. So now that I rewrote 6 plus 10i as a factor, a multiple of two things, I can cancel the common factor in the numerator and denominator. We have a common factor of 2. So I know that 2 goes into itself once, and 2 goes into 34 17 times. So rewriting this in simplified form is 3 plus 5i all over 17. If they asked us to put this in standard form of a complex number, we're not quite there yet because it's the real part plus the imaginary part. And we have just a single fraction. And so kind of go backwards. When you were adding fractions, you needed a common denominator. Let's rewrite this instead of as the sum of two fractions. So I can take the first term in the numerator 3 all over our denominator 17 plus 5 over 17 or 5i over 17. I'm just going to move my I outside of the fraction. So now this is in standard form where I could tell you that the real part is 3/17 and the imaginary part is 5/17. So looking at the next example, we have 6 minus I, and we're dividing by the complex number 4 plus 3i. So if I said simplify the following, rewrite it as a complex number in standard form. So we want to get rid of the imaginary part in the denominator. And so we just saw that we could get rid of an imaginary number by multiplying by its conjugate. But I don't want to change everything. I want it to be equivalent. So I'm multiplying. When I choose that or find that conjugate, I'm multiplying that conjugate both to the numerator denominator. So I'm multiplying by this fancy one. So in the numerator, I'm going to have to distribute. So I have 6 times 4 is 24. 6 times a negative 3i gives me a negative 18i. Then I'm looking at negative I times 4. So that's negative 4i. And negative I times negative 3i. So negative times negative is positive. So that's positive 3i squared. But I squared is negative 1. So that's really going to be negative 3 minus 3. Okay, so multiplying the conjugate, I'm squaring the first term. So 4 squared is 16. Ending up, I don't know if you've seen this, but it's always going to be a plus because the 3 times the negative 3 is negative 9, and the I squared, so negative 9 times negative 1 is plus 9. So combine like terms in the numerator. So 24 minus 3 is 21. Negative 18i minus 4i is negative 22i. All over 16 plus 9, which is 25. And so we're not quite done. We want to put this in complex, standard form of a complex number. And so let's rewrite it as two separate fractions, 21 over 25 minus 22 over 25 I. So there's some properties with a number and its conjugate, or properties of conjugate of a complex number. If you were given that you're taking the conjugate of z, and then that conjugate of z, you take another conjugate. So if you're taking a conjugate of a complex number twice, it ends up being itself. So these are properties of conjugates. Of complex numbers. So for example, if z was equal to, I don't know, 2 minus 10i. So if I was to find the conjugate of the conjugate, well, I know that the conjugate of z is just changing the sign in between the real part and the imaginary part. So I get 2 plus 10i. But if I took the conjugate of that conjugate, I'm going back and I'm changing the sign in between the real and the imaginary part. This would be 2 minus 10i, which recall is what we started with. So that's equal to z. There's another rule of conjugates. If you were summing two imaginary numbers, so z plus w, and then you took the conjugate, it's the same thing as if you took the conjugate of the first complex number plus the conjugate of the second complex numbers. And there's one other one that you might see, which says if you're multiplying two complex numbers and you take the conjugate, this is the same thing like we took the conjugate of the first times the conjugate of the second. So z times w, conjugate it over, so bar over that is equal to z bar times w bar. So let's use these rules to help us simplify the following. So let's say you had z is equal to 3 minus 7i. And let's say that w is equal to negative 4 minus 9i. Part A wants you just to find z divided by w. Well, that has nothing to do with conjugates. Well, actually it does because of what we want to do. So this is equal to our numerator, 3 minus 7i is our z, all over w, which is negative 4 minus 9i. So to deal with this, you're looking at the conjugate of the denominator. So changing the sign in between, we would get negative 4 plus 9i is what we want to multiply both the numerator and denominator by to get rid of the imaginary number in that denominator. So we're just going to distribute. So I have 3 times negative 4, which is negative 12. I have 3 times 9i. Well, 3 times 9 is 27, so that's 27i. I have a negative 7i times a negative 4. Well, negative 7 times negative 4 is positive 28. And then I need the I. And I have negative 7i times positive 9i. Well, negative 7 times 9 is negative 63. I times I is I squared, or negative 1. So I have negative 63 minus times negative 1, which is plus 63. All over squaring our first number. So squaring negative 4, which is 16, ends up as squaring the second piece, negative 9i, or 9i. So 9i times 9i is 81i squared, or negative 81. So we have minus 80, minus a negative 81, which is plus 81. Combining the real parts, negative 12 plus 63, that would give us 51. Combining the imaginary parts, so a 27i plus a 28i Looks like it's 55i, so plus 55i. All divided by 16 plus 18. Not 18, 16 plus 81. That is going to give us 97. So looking at this, we have real part is 51 over 97, plus the imaginary part, which is 55 over 97. So part B, using the same Z and the same W, says that we want to find Z plus W, and then take the conjugate of that sum. So we can either use the rules that we had above, or we can just go ahead and do this. Well, let's just show it that we get the same thing. So if we were to first do this Z plus W, technically that's saying I'm first summing these 3 minus 7i plus negative 4 minus 9i. And once we get that result, we are taking the conjugate. So looking at this, combining my real parts, I have a 3, and this is minus a 4. So that's going to give me a negative 1. Combining my imaginary parts, I have a negative 7i minus a 9i. That's minus a 16i. I still have the bar over those two terms, or that complex number. And taking the conjugate of that is changing the sign in between. So we would get back negative 1 plus 16i. So let's just show if we had done it the other way, where we first took the conjugate of Z and we took the conjugate of W, and then we summed the two, that we would get back the same result as above. So we're looking at the conjugate of 3 minus 7i. So we're going to change the signs there. Plus the conjugate of negative 4 minus 9i. So we're going to change the sign in between the real and imaginary. So changing the sign in between the real and the imaginary for Z, I get 3 plus 7i. Plus changing the imaginary, changing the sign in between the real and the imaginary part, I would get negative 4 plus 9i. So combining the real part, 3 minus 4 is negative 1. Combining my imaginary part, 7i plus 9i gives me 16i. Which is the same thing that we got above, which by that rule or properties of conjugates, that should be true. So one other thing I want to talk about from this section is raising I to a power, a whole number. If we have I, we can say this is the same thing as I to the first power, right? By definition, we saw that I squared was equal to negative 1. If we look at I cubed, well, we can break this down using properties of exponents as a product. This is the same thing as I to the first power times I squared. Well, I squared from above is negative 1. So I really have just I times negative 1, or this is equal to negative I. So I cubed is negative I. I squared is -1. Let's look at I to the 4th power. So we want to break it up into 2 values of I that we know how to find. So I can break it up as I times I cubed, because we just found I cubed above. Or I can break this down as I squared times I squared. Well, I know I squared is -1, so I have -1 times -1, which is +1. So I to the 4th power is 1. If I looked at I to the 5th power, well, this is the same thing I can say as I times I to the 4th. Well, we just saw that I to the 4th power was 1. So I have I times 1, which is I. So I to the 5th power is I. It ends up that I to the 6th power, by following on this route, I would have I to the 5th times I squared, which is -1. You're going to see that these are going to start repeating itself. I to the 7th power is equal to -I. And we'll see that I to the 8th power is equal to 1. So it's repeating itself every the 4th time it repeats itself. And so what we can do, there's a rule that says if you have I raised to some power n, this is the same thing as I raised to r, where r is the remainder of n divided by 4. So for example, let's say that you had I to the 1002 power. So I wouldn't want to go through the process I was just doing up to 1002. So I would use this rule. So let's look at 4 going into 1002. Well, 4 doesn't go into 1. It goes into 10 twice. So 2 times 4 is 8. We have a remainder of 2, bring down our 0. 4 goes into 20 5 times, which gives me 20. Bring down my next number, 2. 4 goes into 2. It doesn't. It's too big. So it goes in 0 times. And so my remainder is equal to 2. So 1,000 and I raised to 1,002 by this rule is the same thing as I squared. And I squared is -1. Okay. So this is the section on complex numbers. You will have some examples in there where you're solving quadratic equations like we were just doing earlier this week. If you get a negative number underneath that radical, you're going to rewrite it, pull out the square root of -1 and rewrite it as I. So some of your solutions for the quadratic equations in this section could be complex numbers.